Well, thank you, Jay. And ladies and gentlemen, I'm sorry I missed the first two talks. We've got some exams going on in our school, and I had to be a dutiful examiner to some students and help them with their projects. So thank you very much, Jay, for the invitation to speak to you today. As Jay said, I enjoy thermodynamics. I'm going to tell you a little bit about it. But the title of my presentation is High Efficiency Photovoltaics, Progress Towards the Ultimate Limit for Solar Power Conversion. So before I begin, I just want to celebrate a really nice project that we have with SKKU. It's funded by KTEP. It's coming to an end, but we've had a great time. And I just thought I'd put up a couple of photographs of a very nice computer modeling workshop we ran on the SKKU campus. We got Professor Yi giving some opening remarks. Then we put the students through 3 days of fairly intensive training with computer simulation. And then at the end, we had a nice party. So I always enjoy these symposia, either in Australia or in Korea. All right, so to come on to high efficiency, why is it that we have trouble making high efficiency solar cells? You know, why can't we make a 100% efficient solar cell? And the answer is because the solar spectrum is very broad. It spans the ultraviolet through into the infrared. So if I was to make a measurement of the solar spectrum in space, I'd measure something like this white curve where, you know, it's in the ultraviolet, goes smoothly into the infrared. It's a pretty good thermal black body spectrum with a temperature about 5,800 degrees Kelvin. Once it's come through the Earth's atmosphere, as I think we all know, various parts of it get cut out, but it still is very broad, and it still is effectively this thermal spectrum. Now, what does that tell us? Here comes some thermodynamics. We have the sun, and we can ascribe a temperature to the sun. Let's say it's 5,800 Kelvin. And we've got the Earth's surface, and let's say the Earth's surface is about 300 degrees Kelvin. And then the thermodynamics is really simple. We have a flow of energy from the sun. Obviously, that's the light, but there's also a flow of entropy, because the sunlight is not sitting at one wavelength. It's not arbitrarily bright either. And so that flow of entropy means that we have to discard some energy if we're going to make free energy work. Electricity is pure work. And so this is then our challenge. We have this flow of energy that comes from the sun, and the amount of entropy associated with that is fixed by the temperature. And so it means that we have to discard some energy in order to convert that energy flow into a full flow of free energy. And so the first person to really do this properly was Peter Landsberg. So he looked at the energy and entropy fluxes that you'd expect from a radiant source like the sun. And then he said, you've got some converter that's at some temperature. So of course, if it's at some temperature, it's radiating back towards the sun with some energy and entropy flux. And so then we can write down some laws of thermodynamics, conservation of energy, and reversible operation. If you like, that's that we can't decrease the entropy of the universe, and we can write down some equations for this, Stefan-Boltzmann law for energy and similar for entropy, and we end up with this Landsberg efficiency, which comes out at 93%. So one of the things I love about thermodynamics is it sits there as this beautiful thing telling us, hey, you could do really well, but I'm not going to tell you how. And then it sits there tempting us, saying, okay, come on, what ideas have you got? How are you going to get to 93%? And so that is one of the things that motivates us with our research, is 93% is the limit. How can we actually get there? So let's come down to a way in which we can perform solar power conversion. And that's, of course, with a semiconductor. I think probably most people in this room are familiar with this. We have a band gap. The idea is we absorb light across that energy gap, and that immediately brings in substantial losses. If we were to walk outside this room and find some random person on the street and say, hey, I want to make the most efficient solar cell anyone's ever seen, do you think we should absorb all the sunlight in in the solar spectrum? They'll say yes, of course. Why wouldn't you? But if we look at this chart, we can see why that won't work. If we take a very low bandgap semiconductor, then yes, indeed, we'll absorb all the photons, but this loss here that we call thermalization is going to be huge. So we get a very large current, we get a very tiny voltage, because the voltage of the solar cell can never be greater than the bandgap. So then, person on the street say, okay, I guess I understand what a bandgap is, which is already maybe quite challenging, but let's assume you find someone on the street who understands what a bandgap is. And then they say, okay, well, I realize I guess I made a mistake. I maybe want a high bandgap. But if you do that, then of course the solar cell's transparent to most of the sunlight. So then you end up with the opposite problem. You get a very high voltage, but almost no current. And so then you say, oh, okay, I think I've got the idea of this game now. We need something in between. And very luckily for us, something in between is silicon or gallium arsenide. And what we find, because we've worked really hard with certain semiconductors, silicon, gallium arsenide, and perovskites are on my chart here too, is that these materials now are operating pretty close to this sort of very idealized picture of a solar cell. This is the Shockley-Queisser model for a solar cell. And this little chart here just shows you the radiative efficiency for different materials with different band gaps, and what that means for the bandgap minus VOC offset, something that we like to call WOC. Now, WOC can be a little bit confusing because the thermodynamic limit to WOC depends on the bandgap itself, which is why my contours here have got a line. This blue line is the radiative limit. You can never do better than that. That just means that for every photon you absorb, there's no parasitic losses. The only thing you can do is re-radiate that photon with perfect efficiency. So we see that gallium arsenide does really well, has efficiency above 29%, silicon's also doing well, perovskites, and so on. Now, there are a few interesting regions on this plot. One of them is labeled Boltzmann. So what about this region here called Boltzmann? This region is what happens if you start to concentrate sunlight. If we take a solar cell, and we're thinking in this thermodynamic way, a solar cell, as we normally make it, looks a bit like this. It absorbs light from the sun, but when we allow it to emit light, that light can go in all directions. And that's actually not necessary. What's necessary is that we can absorb light from the sun, but then we only need to allow light to go back along the same direction. And so there's two ways in which you could think of configuring this. One is to build some system of mirrors and lenses where you just flood the cell with light from all directions. And in that way, you're going to beat this Boltzmann loss. And this is why the efficiency of a solar cell goes up when we concentrate sunlight. Or, if you're clever with optics, you could make some kind of filter that prevents the internal radiation from escaping back to the sun. They're both actually completely equivalent. And so in that way, you could take one of these solar cells here and push it up to about 40%. So single junction limit could go above 40% if we're able to either do really good concentration or if we restrict the angle of emission with a radiatively efficient cell. But you'll notice here that concentration isn't doing too much to gallium arsenide. Silicon actually makes almost no difference. But for gallium arsenide, the red spot here is 1 sun. The best world record under concentration is a white dot. So there's actually a bit of an opportunity there. In principle, that white dot could go up to 41%, but it isn't. Okay, well, let's just take a quick look at silicon. There's been some really exciting progress with silicon lately. I mean, when I started photovoltaics, I was lucky enough to attend the conference where the last really great record from UNSW was announced in 1998, 25% with a Pearl cell. And then there was a long period when nothing happened. And I think a lot of people figured, okay, that's the best we're ever going to do. But then, China has really picked up with manufacturing of PV, but also R&D in PV. And we can see that progress in wafer quality and surface passivation, device architectures have really managed to push both the voltage and the fill factor up a lot. And so there's a very nice paper here from Pinchi Gao's group at Sun Yat-sen University where they've analyzed, why is it that the fill factor is going up the way it is, and it's because our cells are becoming Auger limited. And that's quite exciting. That's pushing silicon as far as it can possibly go. And so, a couple of months ago, LONGi announced this 27.3% efficient cell. The absolute limit is 29.4. So silicon, like gallium arsenide, is getting really close to the limit. Okay, let's just step back for a minute, though, and think about where we've come from with silicon PV. So a long time ago, there was something called a black cell. The black cell is even older than Martin Green, or at least Martin Green's professional life. The black cell is what existed before Martin Green started working on PV. And then when Martin was kind of setting up his group here and doing things with metal insulator semiconductor contacts, IBC was invented. And then there was a period of innovation when what we now call aluminium BSF technology was developed. A lot of that was in the 1970s, EVA encapsulants in the 80s, and then thinner wafers maybe in the 2000s. Then Andrew Blaker's PhD thesis was on something called the MIMP, tunnel contact, metal insulator semiconductor tunnel contact. And that was then kind of reinvigorated by Fraunhofer and ISFH and called TOPCon. And then PERC, the famous PERC cell, came actually after this, and then heterojunction cells. Now, the thing I find interesting here is if we actually look at what got manufactured, it was pretty much aluminium BSF cells up until extremely recently, when PERC was suddenly picked up. And maybe next year, TOPCon is going to be manufactured, become the dominant technology. But what I want to point out is the innovation for a lot of this goes back a long way, yeah? And it also owes its existence to a lot of national programs. In the 1970s, the Americans put a lot of money into this, then Americans kind of dropped off, Japan picked up, then Germany picked up, and now we're in the age of China picking up. One of the interesting things is if you integrate the area underneath one of these learning curves, you get the amount of money that was invested or the amount of money that flowed through the industry. Invested is probably the wrong word. So just the industrial flow of money that drove that technology down that learning curve. And if you do the sums, and it's easy to do, it's not so obvious to look at the graph because it's a log-log scale. But if you do the sums, it's about $800 billion was invested to get us from the black cell to where we are today. But if you look at what was required to get cadmium telluride down to where it is today, it's more like 10 billion. So we often say, oh yes, thin films, what happened to thin films? Why aren't thin films cheaper than silicon? I think the answer is here on this slide. We chose to invest really, really heavily in silicon, and silicon was a technology that could respond to that, and yeah, we've just driven it down this learning curve really aggressively. But as we know, silicon's now at its limits. So where do we go? And I feel this little image kind of represents where we are with PV technology. We're on this sort of local peak, but we know we can get to 93%. That's the top of that snowy mountain. But how are we going to get there? And I think there's many different ways, and at least it's not clear to me which way is actually going to be the best. So for the rest of this talk, I'd just like to talk about a couple of the perspectives I've got for how we might get there. So the first route that most people think of when they think of high efficiency is to make a tandem cell, a multi-junction cell. And so on the left, we just calculated the limiting efficiencies again for a multi-junction cell. The blue region shows you the maximum power you could get under one sun. The top line of this green bit here, which says Boltzmann, is what happens under concentration. And we can see that for practical cells, under concentration or not, so red is unconcentrated, white is under concentration, we can see, yes, the efficiency goes up for the first couple of junctions. But then, I think we've got a challenge in the multi-junction community. Our efficiencies are saturating around about 40% under one sun. And under concentration, we can put up to 47, 48%, but no one has broken through 50% yet. And I think it's actually worth trying to do that, because with 4 junctions, under concentration, we could be above 60%. The reasons why are interesting. We don't have time to go there, but as a challenge, I think, we can be ambitious here. And so the only place where really high efficiency multi-junction cells get used is either in solar concentrator systems, where commercially you can buy cells with 40% efficiency, or in space, where these multi-junction cells are used to power spacecraft and typically have about 30% AM0 efficiency. Now, one of the names of the game if you're trying to make a multi-junction solar cell is to balance the photogenerated currents in the component cells. I'm showing an example here for a triple junction cell. So, for example, you might have a low bandgap material that absorbs a lot of infrared and generates some photocurrent. Then you have an intermediate bandgap cell that generates something in the middle, and then a high bandgap cell on the top. You have to carefully adjust the threshold of these materials. Now, people tend to then go away and make very complicated alloys, you know, quaternary, pentanary alloys, and say, okay, yeah, I can change band gaps using this material. When I started out in research, I ended up in a research group that was looking at these sort of very thin bilayers of ternary material, and we were integrating them together so to make a sort of kind of composite. We called it a quantum well solar cell, but you know, the quantum bit doesn't really matter here. What we're doing is we're just combining bilayers, and these things are, you know, only about 8-10 nanometers thick, you know, to make something that has the electronic properties of something in between and the structural properties of something in between. And at the time, I got a lot of criticism. People said, Ned, this is way too complicated. Who on earth wants to make a low-cost technology like a solar cell using such a complicated structure? But the interesting thing is that it actually worked, and it turns out that structural complexity in a solar cell is easier to control than chemical complexity, at least for 3-5 cells. And so the highest efficiency solar cell anyone's ever made, you know, and credit to the research group at NREL, who are magicians when it comes to growing cells with epitaxy. They took this strain balance concept, made this really beautiful intermediate absorber, which is what you need to improve the efficiency of a triple junction cell, and got 39.5% under one sun and 34% under AM0. And so that's nice. You know, this strain balance idea produced a world record, but it actually is also flying in space right now. So Boeing Spectralab use it in their high efficiency 32.2% space cell. So what observations can we make of, you know, from what we've covered so far and PV manufacturing? I think with tandem cells, what I've learned from 3.5s is that, you know, structural complexity is actually easier to control than we might think. We're beginning to see some silicon cells that are really quite complicated. TOPCon, for example, was written off in the early 1980s. Martin Green figured it's going to be too complicated to control this really thin this really thin oxide layer, tunnel layer. But then we have ALD, and then ALD enables these advanced silicon architectures to be made. Okay, so I think structural complexity is something that in photovoltaics we're learning how to cope with. The other thing, which I've hardly had any time to talk about, is I think actually 3.5 PV doesn't need to be expensive. It is expensive because it gets used for spacecraft, but it will never be as cheap as silicon, but it can be driven down a learning curve in a similar way to silicon if we want to. So it brings me to the second part of my talk, which is, okay, we talked about high efficiency, but what about low cost? So the Australian government's got this strategy, 30-30-30. They're pushing us to generate really low-cost electricity because we need low-cost electricity if we're going to make green hydrogen. So the stretch target is $15 per megawatt hour, and they've given us mission impossible. More than 30% efficiency, less than 30 cents per watt system cost, which means the module cost has to be a lot lower than that, and it has to be achieved in the next 6 years. You know? That's going to be interesting. So when you look at ways in which you could improve efficiency, if we're going to get the cost down quickly in 6 years, how are we going to do it? I think we're going to have to do it and build on silicon. And so there's lots of different things we can do. There's 3.5 silicon tandems. So our nice project with SKKU is on one of these. There's perovskite silicon tandems, which we'll hear more about today. I want to focus on this up and down conversion. If we think about what a tandem cell is, it's something that absorbs 2 photons for every electron that flows in the external circuit. It absorbs a blue photon and a red photon. And as we've discussed, it's really important to match those two currents in those two subcells. Okay? Upconversion is when we have a single junction cell, but we put something behind it that will absorb two red photons, and then there's an interaction between those two absorbers, so that then you produce the sum of the energy and you can radiate that up into the cell above. Upconversion at first looks interesting, but I'll tell you why it's flawed in a minute. Downconversion, on the other hand, you put something on the top of the cell, it absorbs blue light, which has an excessive energy, and then you can produce two excitations from that. So you effectively split the energy in your high energy photons. Now, what's wrong with upconversion? Upconversion requires you to have two photons that arrive simultaneously. Now, what do I mean by simultaneously? It means that I've got something which I can excite, and then I need to have a neighbor which I can also excite within the lifetime of the first excitation. So then you ask yourself, okay, there's a lot of photons in sunlight, surely that happens. And the answer is no, it doesn't. When you look at nanosecond timescales and relatively small bandwidths, you find that actually photons are going to arrive within a few nanometers about once every millisecond. So that means that the excited state lifetime you need for those upconverting systems is about a millisecond. And there aren't very many materials that absorb and emit light strongly that have lifetimes of milliseconds. So there's a bit of a challenge there with upconversion, because the photon flux that we get from the sun is relatively sparse. Photons don't arrive very often on the nanoscale. On the macro scale, square meters, yes, there's incredible 10 to the 21 photons per second per square meter. Yeah? But on the nanoscale, they don't arrive very often. And that's going to be a problem if you're trying to add together the energy that you receive in photons. But luckily, downconversion is the opposite. For downconversion, what you need is for you to absorb a photon and for the neighbor not to be excited, because then you're going to want to interact with your neighbor and produce two excitations. So downconversion actually works well with the sparse photon flux. So as a result, when we're thinking about how we're going to meet this Australian target of 30%, at really low cost, and in 6 years, it seems like downconversion might be a good way to do it. And so we've got a big project which is doing something called molecular singlet fission, which is a molecular means of performing this downconversion. So the idea is that we absorb blue light and then we split it into two excitations, either directly into the silicon, or we produce two red or orange photons that get radiated into silicon. Very briefly, because I think I'm out of time, how on earth does this work? If we look at how molecules are configured, molecules have a ground state, but then depending on the spin configuration of the electron in the excited state, you either have a singlet state or triplet state. When we absorb light in a molecule, we'll just excite an electron and the spin of that electron won't change. So that means it goes into its singlet state, which is always higher energy than the triplet state. Now, if I have two molecules next to each other and I excite one of them, and importantly, the triplet state is sitting halfway between the ground state and the singlet state, then I can have an interaction. And that interaction can flip the spin of my electron in the singlet state, lift the electron in the adjacent molecule up, and then end up with two molecules in their triplet state. So this is singlet fission, and it occurs in many, many molecules where the triplet state is located approximately halfway between the ground state and the excited singlet state. So our project is effectively applying this to increase what is effectively the quantum efficiency above 100% over sort of the short and sort of, well, I would just say short wavelength range here. Now, in the interest of time, I think I'll have to skip a few slides. But, what can we observe from thinking about how can we get to high efficiency at low cost? I think obviously tandems are one approach. Almost everybody talks about tandems. I think we should also think of other ways. And the best I can do is to suggest that we might want to do some kind of carrier multiplication process like singlet fission. Now, last of all, Is there anything else we can do with sunlight? When we think of solar energy, we, of course, think about trying to harness the energy from the light that's beating down on the Earth's surface during the day. But what's happening all the time is the Earth is radiating in the infrared out into space. So, as I've shown with this little diagram. And so, when I visited the Opera House a few years ago with a thermal camera, as you do, I mean, I'm sure when you go and have a nice dinner, you take your thermal camera and you take pictures of the Opera House. But if you were to do that, you would find that the Opera House is glowing rather nicely in the infrared. And that's not just because there's heat being generated inside the Opera House. It's because all the heat from the day has been absorbed in the concrete steps, in the water, even the bridge is glowing. But you notice that the sky is really cold. And so there's actually a way we can generate energy from this. If we go back to thermodynamics, we've got here radiant heat flow from the Opera House or the steps into that cold night sky. And from thermodynamics, we know that whenever there's a temperature difference, concrete and cold night sky, we can generate some electricity. And so we can write down some maths, just as we did at the beginning of this talk, and we can say, yes, this is possible. But thermodynamics teases us. It says, yes, that should be possible, but I'm not going to tell you how to do it. And that's the fun thing. So if we think about solar energy conversion, of course, it's hot sun, cold earth, and we put the converter on the cold side. That's what a photovoltaic solar cell is. But there's a class of devices called thermoradiative devices where we do the other way around. We put the converter on the emitter side. Thermodynamically, there's nothing unusual with this. It's just we tend not to think about doing energy conversion, radiant energy conversion like this. The easiest way to think about this is, for example, these deep space probes where we use hot plutonium pellets and then heat flows through a thermoelectric and then it gets radiated out into space, so you have a physical temperature gradient. That's a thermoradiative device, and we've been doing that since the 1960s. But what we managed to show was a semiconductor device that does this spontaneously, without any thermal gradients. So that's a thermoradiative diode. And in my last minute, I'll show you how this works. So we did an experiment that looks, with hindsight, quite simple. We have a mid-infrared diode here. So this is a low bandgap semiconductor. The bandgap is 0.25 eV. If we put it in front of a hot source, it behaves just like a photovoltaic device. I get a negative photocurrent, I get a positive photovoltage. Now if I reduce the temperature of the surface it can see, the current goes down and the voltage goes down. And when the two are at the same temperature, I get nothing, as you would expect. But then if I keep reducing the temperature of that surface, something incredible happens. We start getting a positive photocurrent and a negative voltage, which means that we're generating power by emitting light from something that's warm into something that's cold. But all it is a low bandgap semiconductor that's radiating thermally. We're very comfortable with that. And it's just that that semiconductor is warmer than its radiative environment. So it turns out this thermoradiative diode has been sitting there all the time. But it's only in the last couple of years that anyone's actually done measurements like this. And one of the reasons for that is because the voltage is very small. Yeah, we're measuring hundreds of microvolts here. So it's not like you can go to a solar simulator and just measure this. It took a little bit of effort to make these measurements. But the power densities we're getting are relatively low because the temperature differences we're dealing with here are relatively low. Milliwatts per square meter. In principle, you can get up to watts per square meter if you were to do this really well. But what we have today is enough to power a little wristwatch like this from body heat. And in principle, as I say, solar PV is always going to be more powerful than this thermoradiative approach. During the day, the highest efficiency we're likely to get is sort of the orders of many hundreds of watts per square meter from a solar PV device. These thermoradiative devices can give us, maybe a few watts per square meter if we do a really good job. Right now we're at milliwatts per square meter. And so I'd just like to finish with a perspective. I think one of the first places we're going to be installing these thermoradiative diodes is on spacecraft. And there's a nice historical parallel. The first silicon solar cell was published in 1954, and here are three gentlemen crowding around their new invention. But by 1958, they put that silicon solar cell on a spacecraft and powered it. And so when we think, that was back in the 1950s, people had to do maths with slide rules. They didn't have computers, yeah? But they went from, I don't know, TRL 3, 4 to 9 in 4 years. So I really think this challenges us with the thermoradiative diode. We made our publication in 2022, which means I've got until 2026 to actually do this. Otherwise, I'm going to feel that, you know, we're maybe not working as hard as these guys were in the 1950s. So I'd just like to conclude, you know, I think when it comes to thermoradiative diodes, we're very much at this stage where silicon was in the 1950s. You know, it was a nice landmark result, but people weren't quite sure what to do with it. But we all know what happened with silicon photovoltaics. You know, we chose to take our team photograph in the mid-infrared because we can. And as I say, our challenge is to try to push up the power density of the thermoradiative diode and, you know, try to get it into space in the next 2 years. So if I've got time for questions, very happy to answer them. Thank you.
Thank you for a very nice talk. Any questions from audience? You mentioned about the down conversion can be a possible way to achieve higher efficiency with low cost.
Yes.
So how do you estimate how much will be the efficiency gain from the down conversion and how it can be achieved with the low cost?
Yep, great question, thank you. So I'll give you the practical limit first. So our calculations show that we should be able to get to about 33%. So we take a really efficient silicon cell. So let's take that cell from Longi that's already 27%. If we make sort of similar assumptions, you know, that it's going to work really well, it can push it to 33%. Now, we need to be careful because if you take these thermodynamic limits, you actually end up with an answer of 42%. But that is already taking a baseline cell that's more efficient than silicon could ever be, because silicon's limited by, you know, Auger, as we discussed earlier. So, yeah, the opportunity with this down conversion, this singlet fission, is to push up into sort of low mid-30s. One of the things that I didn't mention, but I think is actually quite important, is that because these carrier multiplication approaches just add to the photocurrent of the device, they can be improved incrementally. So if, for example, we produce something that adds 1% efficiency to a silicon cell, that's already very valuable. You know, the industry will love that. Whereas when you're trying to make a tandem cell, as I know too well, trying to make high-efficiency 3-5 tandems, is each of your subcells has to be really high performance before the overall efficiency of the tandem is good. So in a sense, the challenge with tandems is you have to almost reach perfection before you overtake the cell you're trying to improve. And I mean, that's been achieved, obviously, with 3-5s, it's been achieved with perovskites, it's been achieved with, you know, several materials. But in terms of manufacturing and large-scale scale-up, you know, those, of course, are still challenges. Plenty of challenges with carrier multiplication too, but one of the advantages we have is that we can incrementally improve the carrier multiplication process, and that is useful with every step we make in improving that process.
Is there any potential material that can be used with low cost?
Yes. So I've got a whole load more slides on what we're doing in our project, which I knew I wouldn't have time to show you. One of the things which really inspires us is one of the most stable organic pigments that we've ever made is a molecule called Ferrari red, and it's used, unsurprisingly, as red car paint. Now, it's stable, and obviously we like it because we can make cars colored, and people like that. But Ferrari red and similar molecules actually have almost exactly the right electronic structure for singlet fission. So one of the challenges, but also opportunities that we have, is taking molecular structures that we know are stable and then engineering them so that they can perform singlet fission efficiently. And singlet fission has actually been known for a long time. It dates back to the 1960s. But it's only very recently that we've really tried to push these two things together and apply them for silicon photovoltaics. So Yes, I think we're confident that we can make these molecules that we need at low enough cost to hit those cost targets. Of course, today, if we show you what we're making, yeah, it's very small scale in the lab. But in principle, the molecules we're making are similar to automotive paints.
Any more questions?
Thank you for the nice presentation. Professor Lee asked about the down conversion. So my question is about up conversion.
Yes.
As we know that the down conversion compared to the down conversion, the up conversion is not that advantageous in achieving the internal quantum efficiencies. Because as you mentioned, that we need to make some multiple acceptors or sensitizers to work as a synchronized manner.
Right.
So what do you think about, is there any possibility that we can use these kinds of the conversion nanoparticles assisted with some plasmonics or photonics, which can be integrated into the thin film photovoltaics or something like that? Because I have experience about these kinds of the research based on the sodium, ytterbium, boronitride, something, fluoride, something like that. Yeah. And I found that it is internal quantum efficiency is less than 1% or max tops 2%. So to use this near infrared or mid infrared up to 2 micrometer wavelengths, I think that we need to make some kind of optical path length elongation or some kind of integration of these kind of the layers based this conversion nanoparticles or core shell nanoparticles. So we tried so many different various steps to increase this kind of IQE, but it is very hard to achieve this kinds of the substantially the high internal quantum efficiency. So what do you think about this kind of possibility using conversion materials?
Yeah. So, yeah, the challenge with upconversion, as I mentioned, is that we need to have those two excitations in the same interaction volume. And so you can then say, okay, what can I do? Let's say that you're going to keep the photon flux the same. We're not going to concentrate sunlight or use laser beams. So then you say, okay, the only thing I can do is either increase the excited state lifetime. So you mentioned using rare earth ions, and they have very long lifetimes. The only problem with rare earth ions is the optical transitions are forbidden, so then they're weak. So that means they don't absorb very well. So then the challenge, which I think you've alluded to, is that you want to try to sensitize those ions so that they can absorb more strongly. And that is one of the possible pathways you might be able to solve this problem. Because what you want is to say, okay, I've got these big antennas that can absorb photons, and then you want to funnel the energy to this little sort of reaction center. And I'm deliberately using words that are similar to photosynthesis, because that photosynthesis is remarkably clever, as we all know. I mean, we still don't fully understand it. But I think the way in which upconversion might work is if we have these big sort of harvesting antennas made for whatever way. I mean, plasmonics or kind of metals might be one way, but you could probably think of molecular ways of doing this too. But then you perform the upconversion process in a much more restricted volume. And that way you've kind of increased the interaction area, and you can harvest photons that wouldn't otherwise interact if you've got one absorber here and one absorber here, and they're far too far away for that interaction to take place. So I think it's possible to think of ways in which you could make upconversion work. It's just, I think it's a lot harder than down conversion, because down conversion, you're already playing into the benefit you have that the photon flux is so sparse. So the chance that you absorb a photon here and your neighbor is also excited, which is not what you want with down conversion. You want the neighbor to be unexcited, that plays naturally to your advantage. So for sure, let's talk about how we can make upconversion more efficient, but that's a struggle.
One quick additional question. So you mentioned that the solar incident radiation fraction can be decomposed into some kind of the power output or Boltzmann factor or some current cycle, something like that. So in terms of a conversion process assisted by the plasmonics or photonics based on the final resonance or pulsar effect or some favorite ferro resonance, something like that, do you think that we need to rewrite the physics considering this plasmonic effect some local or micro scale?
No, I think the physics is still good. I think where we've been a little bit, how to put this, where we've perhaps overlooked something is that we've tended to assume that sunlight is this continuous flow of energy. And it's only when we start thinking about the problem in terms of lumps of energy, photons that arrive actually quite infrequently, that then we have a problem. So we can do all these beautiful experiments with laser beams and everything works, the physics works. But the trouble is that when we go to solar photons, we then no longer have these really sort of, continuous beams of light. So in other words, if I think of a laser beam, I don't even need to think about the fact it's composed of photons. It's a flow of energy at some wavelength. It pumps a system. I can use a rate equation. And if you do that, then you say, yes, this should work. But then when you say, actually, no, that laser beam or that sunlight has got now discrete photons that arrive, and then there's a great long time before the next one arrives. When we look at that level of detail, then we realize, yes, these continuous rate equation thinking needs to be modified. So I think the physics is fine. It's just that we've historically tended to neglect, if you like, the quantum nature of light.
Thank you.
You're welcome.
Thank you. Let's thank the speaker again.
Okay, thank you.